Welcome everyone. It's my pleasure to welcome René Vidal. So René is a professor at Johns Hopkins University. I'm not going to go through his bio. It's in the in the talk announcement, and he has been a distinguished researcher working in optimization and control and applications to various problems, including problems in medicine. And as some of you may know, René will be joining Penn starting January, and he's going to direct the new ideas initiative that we have here. And he'll be a professor in ESC and radiology. So today he's going to tell us about explainable AI. So welcome.
Thank you, Rajiv, and congratulations to Penn on creating Asset. I think it's a great initiative and look forward to working with all of you on this. I think this is maybe the first work that I do that connects to explainability. So I'm maybe new to the field and I'm going to be learning. And so happy to have feedback and discussions and questions that we move along. So over the last decade, machine learning and deep learning has had a great impact both in academia as well as in industry. And as time progresses, it's moving more from academia to industry, and many applications are impacting our lives, from self-driving cars to speech recognition to, say, Amazon Go. And so as applications of machine learning are deployed in our real lives, it becomes increasingly more important to make sure that those applications make predictions that are safe, that are fair, predictions that are robust, but also predictions that to some extent can be explained to humans. And the issue is that by and large, deep networks are black boxes, and they make predictions based on features that are learned from data. And those features are maybe interpretable to some of us who work in this area, but not necessarily to the end user. And so the question is, how do we make those predictions explainable to the user? So when you look at the question of interpretability, sometimes you worry, well, is there a trade-off? In the sense that at the top left, we have maybe the technology that today is highly accurate at making predictions, but is not very interpretable. And in between, there is a rich variety of different machine learning techniques. And typically, it is believed that simple classification rules or decision trees are much more interpretable, but they don't perform as well as what deep networks do. I'll be arguing in a moment that, again, they might be more interpretable, but maybe more interpretable still to data scientists, but not necessarily to humans. And so the question is, how do we really make them more interpretable? I'd also argue that perhaps the reason why interpretability has been focused these days primarily on neural networks is because we care a lot about accuracy. And so ideally, you would like to be on the top right, where you are both accurate and interpretable at the same time. So because the current focus has been primarily on accuracy, the type of interpretability is being what is called post hoc. Namely, you have your training data, you train a model, it makes predictions, and once it's been deployed, you try to interpret what that model does, right? And the issue with that is that there are many applications where this isn't necessarily great. Like the type of predictions or interpretations that are currently made are what regions of the image, say, these computer vision algorithms pay attention to, or in order to make that prediction, which ones are the most important. And then there is this debate as to, well, we look at those regions and do they really make sense, right? And so the good news of doing interpretability post hoc is that you don't compromise on accuracy. You just have the model as it was. But the explanations are somewhat debatable, unreliable, not clear as to why there are good explanations. And it's not clear that in all cases, salient parts of an image are the best explanation to a user. So this has motivated some colleagues to actually question much of the research that's been done in explainability. And in fact, I'm not even sure that there is a universally agreed notion of what explainability should be. Different people think that it's different things. But you know, if we come up with a post hoc method, and then we're debating among ourselves as to whether that's a good explanation or not, probably means that it was not a good explanation. So what we advocate in our work is to do things a little bit differently, and is to think about explainability from the beginning, before you even design and train your algorithm. And so that's what we call explainability by design. Okay, what do we mean by that? The second aspect is really that we think that explanations to a human, to a user, not to a data scientist, have to be in terms of words or symbols or patterns that are interpretable to that user for the purpose that that user is going to use the machine. We argue also that explanations are domain dependent. They're task dependent, they're user dependent. What do I mean by that? Well, the vocabulary, let's say I'm going to give explanations in English, the vocabulary I would use to explain how a medical AI algorithm works, it needs to be based on words that are pertinent to that application. And the vocabulary I would use maybe to explain the decision of a self-driving car would also depend on a different types of vocabularies, but explanations are different depending on the task. They're user dependent because if I'm giving a talk about machine learning to a machine learning audience, I will use certain words. But if I am explaining that, say, to my mother, what do? I would probably give a different explanation. Right? And I guess domain and task I already explained. So how can we capture that notion that explanations need to be adapted to the task, adapted to the domain, adapted to the user? So the way we propose to do that is through a query set. Namely, the user at this level comes up with a large number of queries or questions. At this level, for the sake of simplicity, suppose that are binary, yes, no type of questions. And those questions have to be, if I'm able to answer all such questions, or if the algorithm is able to answer all such questions, then the user is going to be satisfied. So in a certain sense, there is this notion that this set of questions or this query set needs to be sufficient for that task and for that domain. And therefore, an explanation for the prediction that an AI algorithm makes would be obtained by composing or by conjunction, say, of a series of questions and answers. So that's the overall idea. And so just to provide one concrete example about something I don't know anything about, is how do you classify birds? And so if you go and ask experts how to classify birds, well, they look at a long list of attributes, and they just ask whether that attribute is present or not. So it could be, for example, whether the bird has a throat color that is yellow, right? And every time that one of these questions is asked and you get an answer, then you split the space of possibilities, right? And basically, this is immediately sort of suggesting something like playing a 20 questions game, where at the beginning I would, they'd have to come up with some question. If I'm smart enough, I'll probably try to come up with a question that splits the possibilities half and half. And then given the answer, I'll ask a second question, and so on and so forth. And typically, even though the number of attributes might be very large, say hundreds or thousands, or maybe the number of queries might be even 10 of thousands, it turns out that generally speaking, you only need a few queries. 10, 20. Well, 20 questions for a reason, the game, right? Because typically you need 20 questions in order to actually make a solution, right? So that's, I think, at a high level, the goal. And also, just to finish with this slide, I've written here smallest number of queries. I'm trying to capture the idea that simpler explanations are to be preferred to longer explanations. So that's why we're going to be trying to look for the smallest number of queries. We are going to propose to do that using information gain in the sense of the most informative questions for making that.
Are the questions about the feature vector only or about the classification decisions as well? I don't quite understand that.
At this level, the questions can be fairly broad and application dependent. And I'm going to be giving a bunch of examples of queries that we have selected, but I can tell you the questions could be simply about selecting features. So it could be, what is the intensity of this pixel? Or what is the color of this pixel? Or give me the intensities of this patch. It could be in a document, is this word present or not? It could be attributes, like in the case of images here. Or it could be questions about the presence or absence of an object in an image as well. In the medical domain, think about, you ask the patient whether it has this symptom or not. And so at this level, there is just a large set of query set that is given to me, and it is application.
Maybe this will become clear when you get the model, but what I'm missing is the connection between the explanation and the model it's explaining. So is the premise that the model it's explaining has to predict green J on every example that has this particular set of answers?
So it will become very clear once I go through the framework, but at a high level for this particular example, the task is simply classify the bird species given the image. And the way by which the classification is done is, rather than training a deep network, that's the classification, we are going to be asking one question, given the answer, we'll select question 2. And eventually, and given the history of queries and answers thus far, we're going to be making a prediction.
Okay. So the explanation time is the model.
And therefore, the explanation is the model, because once I'm done, so basically the way it's going to work is, I ask 1, 2, 3, 4, and as I'm asking the questions, I immediately try to make a prediction of what the class is. And eventually, I'll be confident with, say, 99%, and then I stop. And then this is the explanation.
Okay, so it's like a decision tree.
It's not entirely like a decision. It is related, but it's not entirely like a decision tree in the sense that it's built on the fly, and the tree changes for each new image.
And how can, sorry, I think that was my question. Like, if this sequence of answers fixes the classification as green J, then I don't see what it means that the tree changes.
Because every time I select one query, I instantiate a node of the tree. Then the first question will always, I think it is better to have the explanation of the full framework so that I can undo it. So let me get back to that. Okay, so what is it that I'm going to do today? So the work today assumes that these questions are given to me. So an important question and future work is, how do I actually learn automatically the queries? So that's going to be outside of the scope of this talk. I've already said this, that we're going to select the smallest number of queries, and the algorithm is really going to be information theoretic. It's going to be selecting the query that is most informative for making the prediction, and I'll explain what that means in a moment. And it's information theoretic in the sense that we are going to try to come up with new notions of entropy, coding theory, and whatnot. And that begins by redefining bits. And in particular, we're going to replace bits by semantic bits. And these queries that I was just talking about are going to be a new notion of bits. That each, getting a query and getting an answer gives me one more bit of information. And the code, the semantic code, is exactly going to be this sequence of queries and answers. And entropy is going to be therefore the expected number of queries that are needed in order to make a prediction.
So you assume by design that's only yes or no, there's no other.
No, not necessarily. You're going to see in a moment. We need to learn generative models for data, queries, and answers. And whether they're binary or not is how good are you at learning these very complex generative models. Yes.
Are you moving the burden of the queries to the user now?
Yes.
So the user is really putting in all the effort to explain.
Yes, I'm putting the burden. The user gives me a set of queries. The main condition is the user needs to be satisfied. If I answer them all, then the user is satisfied. That being said, for every application I'm going to show, which pixel of the image is a query, I'm just assuming that that's going to be sufficient for interpretation, or which words are selected, or which symptoms are selected. So in practice, we have come up with queries. It's not so difficult to come up with queries.
For your bits, the way you define them, it depends on the list of queries.
Let me postpone the question because that's exactly what's coming. So I'll begin by defining what the bits are and semantic entropy. I'll continue by saying how we compute, how we learn the generative models. And then I'll give a bunch of applications on binary image classification, the bird example that I just talked about, classification of text, and I'll conclude with medical diagnosis. Okay, so let me get to answer some of the questions you're asking. Okay, so we begin with this query set. You can think of query sets as really features. They're functions from the input data to some space. And so I'll distinguish between Q, which is the question, and Q applied to X, which gives me the answer to the question. Okay. So as I said already, we solve a particular task by answering queries about X with the goal of predicting Y. So X here is a random variable that defines my input data. So in the bird example, it's images. Y is what I want to predict. In the bird example, is the class of the bird. And the notion of sufficiency is defined mathematically as follows. At the end of the day, I can make a prediction if I can compute the posterior. I can predict Y given X. And what I'm going to assume is that in the end of the day, I don't need X to make the prediction. I just need the sequence of answers to the queries. And so I'm going to, and that's exactly the notion of a sufficient query set. I said that the prediction of Y given X is the same as the prediction of Y given the set of all X primes that agree with X. Okay. And that's what I define by sufficiency in a sense. So therefore, I don't need to predict Y from X. I just need to compute the answers to the queries. Okay, and so each query therefore defines a semantic bit, and the set of query answer pairs define the code. And this is connected immediately to information theory, right? The code is the sequence of binary bits. So in a picture, and I've already said this, but I begin with an input X, there's going to be an encoder. The encoder is effectively the algorithm, if you wish, or the network or something that is going to select the sequence of queries. I've illustrated this pictorially here by the fact that there could be 1 million queries, but the algorithm just selected 5 of them. Okay. And the order here is not the query number, but it's the order in which they were selected for a particular. And then I need to have a decoder that predicts Y given the code. Okay. And these codes are therefore of variable length. So in various ways, you can immediately, if you're familiar with autoencoders or variational autoencoders, you can immediately think, well, this is more or less what we do today. Or if you're even familiar with information bottleneck. So what's the key difference relative to that? That what we typically call the latent representation, rather than being latent, it's actually this gigantic binary vector of answers to all of the queries. Yes.
So the code is algorithm dependent, right? It's designed.
The encoder is an algorithm that will produce the code. So in classical information theory, you can think of this as Huffman coding.
Right. So that's one specific way.
That's one specific way. Right? But at this level, I'm saying there will be one. How do we find it? It's coming in the next equation. And this is exactly how we propose to find it. So the code is what I've already explained, depends on the query set and depends on this encoder that I was just talking about. This is just the length of the code. So this is the expected code length. And so what we want to do is to find an optimal encoder, the one that minimizes the expected code length. So this is identical to what you do in classical information theory. And we define this notion of semantic entropy, which depends on this given query set, exactly as that, as the minimum expected code length. Subject to the constraint, what is the constraint? The constraint is that the posterior, so the prediction of y given x, is the same as the prediction of y given x. And that's the sufficiency. So this is very much related to what people have been advocating of minimal sufficient representations of data. Stefano Soato has a couple of papers. With the main difference here, again, that we have this extra constraint that the code is not latent, but rather semantic and meaningful data in this case. Okay. Now, the next question is, well, how do you solve this optimization problem? That could be one. In fact, it's intractable. It's easy to write down, but it's not easy to solve. The other one is, well, okay, is this related to information theory in any way? What are the connections? Are there cases where this reduces to classical entropy or mutual information? So the details are in the paper, so I'll skip them, but I'll just present for you, those of you who are more theoretically inclined, what are some connections. So if what I'm trying to predict, y is equal to x, which is sort of a reconstruction task, then the semantic and q is that I am allowed to ask all possible binary queries about it. Then semantic entropy is the same as entropy, as classical channel entropy. Yes?
So I'm trying to understand. So the optimal code here is the Hopkins for this?
No, half-one coding, first of all, is only within 1 bit of.
Yeah, so that's my question. How do you say it's exactly? So all the binary questions, all the possible binary questions, all the possible binary
Yes,
questions?
that's what it says. Q is a set of all possible binary questions.
And that gives you exactly. You don't need any block thing.
The second result is that if x and y were random variables thus far, but if one is a function of the other, and again if you use a set of all possible binary queries, then you can show that semantic entropy is within 1 bit of entropy. Okay. And the third, and this is I don't know whether this be useful for anything, so hopefully, I think for those of you interested in information theory, sort of properties, it's not negative, independent assumptions. I conjecture that this additivity could be connected and useful later on for measuring complexity of tasks, and especially when you put together, here I'm trying to predict 2 variables out of the same x, and this is saying that the semantic entropy of the 2 tasks combined is less upper bounded by the sum of the semantic entropy. Okay, so that was a little bit the tour about there are some properties, even though in simple cases, right? The other important thing that is important to highlight at the theoretical level is that the encoder, if the encoder is given, it really what it does is to partition the input space into a collection of equivalent classes, namely the set of all inputs that have the same answers to the set of words. Okay. In the case of an image, for example, suppose that I simply pick one query, and which is 1 pixel, and I said, and the color is red. Now it's like find all of other images that for that pixel is also red. That would be for that equivalent classes. Okay.
How is it related to quantized like VA, where you also have like words, quantized set on the bottleneck of the encoder, and you can do prediction based on quantized set?
Yes. You mean the vector quantized VA? Well, the vector quantized VA, the variables are latent. They're cluster centers. They don't have a semantic meaning, so they can't be used for interpretation. unless you assign an interpretation to the class itself.
But all these definitions here, and interpretation did not.
They do from the perspective that Q is a query set, is a question and answer. Okay. And so we conjecture that this notion of semantic entropy could be related to task complexity in the sense that the number of equivalent classes with these query set partitions, the input data, could be related to task complexity. And so, in fact, we have another little theorem there that if you have a finite query set, in this answer your question, do they need to be binary valued? Here is b valued. The number of equivalence classes is on the order of b to the semantic entropy, and this is sort of the typical quantities that appear in generalization bounds. So we don't know yet, but we conjecture that there could be ways of deriving also generalization bounds for semantic tasks using semantic entropy as the measure of complexity. Okay, let's go. That was a little more theoretical detour, but the talk is meant to be a little bit more practical. So let me go back onto what do we do with what I've said thus far. So what I've said thus far is, okay, we propose to find an encoder that, given the data, is going to tell me what queries to ask. And then given the queries, we're going to make our prediction. And if we're able to do that, then we'll have an explanation for every prediction. But computing semantic entropy is generally intractable. And so we have to make some compromises. One thing that we want to take advantage of is the fact that even though I could have a million possible queries, in order to make an inference for a given input, I just need a handful, maybe 20 questions. And so that motivates the idea of doing this sequentially and in a greedy manner. And so this is what the information pursuit algorithm is. And it's a well-known algorithm from the 80s. So the idea is going to be the following. At the very beginning, I am going to select the query that is maximizes the mutual information with respect to y. That's going to be the first query. Okay. The other day, I was talking to my 9-year-old at home, and I said, "Oh, I have a number between 1 and 10 in my head. Ask me a question." And he said, "Is it less than 5?" And I said, "Why did you ask me if it is less than 5?" "Oh, because that's the device. Then it's you get half and half." So that's exactly the idea of the first query. That the most informative ideally would be something that splits your space in half and half. You need a probability model for that, but that query you ask it without looking at the data yet, right? The x and y's here are random variables, so you just need your generative model. So the next query, though, the second one, is you also choose it to maximize, is the most informative query. But now, given the fact that I have the first query and I have the answer to the first query. So going back to the guessing name, if I tell my son that it's less than 5, then he'll probably ask me next whether it's less than 2 or 3, I guess. Yes.
These are semantic mutual information or the actual?
This, again, whether it's semantic or not depends on what the queries are, right? If the queries are semantic.
What
I? No, this is regular mutual information. This is Shannon mutual information.
And this is just building a decision tree.
Huh?
This is building a decision tree.
This is billions. Yeah. Now, if you are a statistician, then you will be worried about what I wrote here, right? Here is little x. So this is the particular image that I'm looking at. And so this seems, you don't condition on that. So again, this is the equivalence class. It's the set of all x primes that agree on all answers. That's fine. And then eventually I will add to the queries a stop query. And when do I stop? I stop when the mutual information between any query and y, given the queries that I've seen thus far, is 0.
You do this separately for every y? Because in the beginning, you don't know what the y is, right? It's a random variable.
So the y is a random variable. So this is just computing the mutual information on the joint distribution of X and Y. Okay. So this is great and nice, and so it's all good. And that's the exact algorithm. In practice, you might want to stop in a different way. You might want to stop when your posterior is sufficiently thick, or when your posterior, when you get to 99%, maybe I'm happy. So you could do variations, or you could, things like that. But to implement all of these, I need to compute the mutual information. And to compute the mutual information, what do I need? For the first query, I need the joint distribution of Q of X and Y. All right. And for the next queries, I need the joint distribution of X and Y given the query that's part. So I need one generative model here. And then I need many generative models, one for each possible history. Okay, so you can immediately begin realizing, okay, you made my life easier, it's computationally better, but still this is fairly intractable. So if you make assumptions about your model, there are Gaussians and things like that. Right, but we want to do this with images. So we're talking here about complex things.
Which class of optimization problem is the next to you? Because usually the architect like sensing or next measurement, different stuff from like dynamic programming, Monte Carlo presets up to submodular.
No, here, for the sake of simplicity, let me just do the simplest thing. This is not really at the end of the day division optimization problem for. So if Q is simply a set of queries and I have 20 of them and they're binary, all I'm going to do is simply evaluate mutual information for each one of them and then select it. So cases where you need to do optimization might be for maybe continuous queries. Let's say that the query is actually a hyperplane that separates them, and then you need to do optimization. So in fact, PCA is a particular case of all of this. If the query is selecting the direction, this would give you an X and Y, an X is equal to Y, and there are Gaussians. This will give you the first principal component, and so on and so forth. But at this level, I'm really thinking discrete and just evaluating. So the challenge is learn your generative model, and can you compute mutual information efficiently and reliably? Okay. So I've already said this. This remains intractable. This remains difficult because you need this joint distribution of Q of X and Y given history. Extremely hard to estimate empirically. Think about X being images. Even harder because the conditional part is terrible. Namely, if you have imagine you actually had a huge training set. So you could learn the joint generative model of Q of X and Y. But once you condition, right, it's like you restrict your training set to all of the images that have pixel 25 equal to red. And as you add more and more queries, your training set just keeps reducing. So this becomes increasingly harder to train. So it would probably take me a good 15 minutes to really give a good explanation of what we do, and I don't have the time, so I'm only going to have half a slide on it. So I'll try to say a few words. What we do is to make assumptions that make learning these models a little bit more tractable. One assumption that would make our life super easy would be to simply say all the queries are independent from each other, or all the queries are independent from each other given Y. But those assumptions end up being too strong. So what we've done here is to simply postulate the existence of some latent variable so that the queries are all conditionally independent, given that latent variable and given Y. And when we do that, you can formulate the problem, and one particular choice of models is to use variational algorithms. So what's happening here? The input here is the query and the label. Okay. So if the queries are just asking the pixel intensity, this is really the input is the image and the label. You map it with a probabilistic encoder to a latent variable. The latent variable here is simply assumed to be Gaussian. And the network, what it does is to predict the mean and the standard deviation of that Gaussian. And again, the decoder, you sample from this Gaussian. It's also conditional on the class, and then you make a prediction of the queries. So in the case of images and in the case of the query set, just asking about the pixel intensities, this is really just learning a joint model of images and data. Okay. There's lots of more details because to learn these adequately, you need efficient MCMC. We've tried a variety of things. We've settled with doing an adjusted Langevin, but for some time we also did flows and things like that. But okay, this becomes just your choice of how you learn good generative models for your specific problem. Yes.
Can we intuitively say that the term y given x is equal to the y given z? So z has all the information that we need from x about 1.
I'm not so sure. I would probably need to think about it. The way we thought about it when we designed this was that more that z were nuisance variables. So in the case of image classification, there might be variations in lighting and viewpoint and things like that, but they're latent. So they capture the. In other words, for example, right, the decoder, let's say, generates an image given the class. And now the z variable captures all of the variability of images of that class. So that's why I'm not sure. Yeah.
So I want to understand, I guess, like, what is the claim about what makes the model interpretable? So if I'm understanding things so far, the user provides a set of features, basically.
Yeah.
Queries, and then you're building a decision tree by splitting with the decision tree on the features proposed by the users by splitting with this sort of information.
Mm-hmm.
Is the claim that any shallow decision tree on the features proposed by the users is interpretable, and that the splitting criteria is sort of a heuristic to try to get a shallow one, or is the claim that it is only interpretable because you are splitting with this information?
The latter. That is interpretable because I'm splitting with this criteria. And in the paper, for example, for the case of birds, we have an example where we train a decision tree, and then we take one node of the decision tree and we ask to split the data, provide sample images where the answer is yes, provide sample images where the answer is no. And at the level of humans interpreting those results, it's hard to parse what the two groups are. While if the query is does the bird have a yellow belly, then you look at the images and you clearly see the separation.
So that's based on the splitting being based on the queries provided by the
Yes,
user.
exactly.
So that I understand. I
Yes.
understand that you want to split on queries based on the user, and that's one source of interpretability.
Yes.
I guess the question was, if I manage to come up with a shallow decision tree that branches only on the queries provided by the users, but I did it with some other algorithm, not using mutual information. I did exhaustive search, and I found, like an accurate short decision tree.
I
Would that
think
be
in
it?
terms of interpretability, that would probably be also fine. It is again the question of even though we can't compute the optimum, that we are trying to claim that you are trying to do it with the minimum number of possible queries. But you're totally right.
So just to encode it,
Yes.
the claim about interpretability is this, that we are interpretable if our model is a shallow decision tree that branches on the queries provided by the user, and then this is a proposed algorithm to come up with it, but the details of this do not interact with the claim about interpretability.
Yeah.
So I understand that you're using a subset of the queries provided by the user that partitions as you need it. Is the goal, and the goal is to make a small subset along any one path. Yeah. But there's also the goal that if you get the union of all the queries in the entire tree, that should be a small subset. Meaning you don't introduce different queries on different paths, or should you, or is it not a goal?
It was not a goal, and it's the first time I'm thinking about it, so I wouldn't know whether that's a good goal or not. Yes.
Just notation, so your big Q of X is the vector of all the queries for X.
Yes,
Like so it's a random variable.
yes, I should
Right,
have made
and
it.
it's equal, so it's also equal to that little.
Yes,
Yeah,
these.
the random
and
variable.
that one. Yes,
No, I meant the one up there. Did you use little Q
Yes.
with big X there?
yes,
So
yes,
that's-
yes. I guess the only distinction is, yeah. I apologize for the notation, so the X's and Y should all be capital. But the little q of X up there means one query, while the capital
Oh,
Q
I see.
means all of them here. That's the Q's word.
I'm just trying to understand, where does the semantic definition go here? So Z, you said, is just a nuisance.
No, so this is the semantic information is not here. This is a particular algorithm simply to learn a generative model that relates data to queries and queries to predictions. Once I have that generative model and it's trained, I use it with information pursuit to compute the first query, the second query, the third query, and eventually I stop. And I get the semantic information by running information pursuit.
And I guess, I mean, that's people have been training decision trees for a long time. So like, does this come up with shallower decision trees that you ran? I don't know,
Yes.
4.5?
Yes, we did those experiments. Yeah. Yes. Okay, so let me give you a few examples. The first example is relatively trivial and almost stupid, right? The task is the simplest possible. It's classify the administration. Why do you want to do that when you can train a network that does 99.9999? Well, the idea is to do it in an interpretable manner. And in this case, what we're going to do is that the queries are going to be the image intensity is in a small patch. The size of the patch is irrelevant, could be pixels or 2 by 2, 3 by 3. For whatever reason, let's say I choose 3 by 3. And so the idea is, you've not looked at the image yet, can you classify it? Okay. No, then I'm going to select one, which 3 by 3 patch will you look at? Okay, I'm going to look at this one. Okay, now that you looked at it, what number is it from 0 to 9? How many such patches do you need to look at in order to classify? That's the way we're going to do it. And therefore, we're going to produce a sequence of patches that the algorithm looked at in order to predict what class it is. And then, of course, I introduced that with the MNIST, but it can be done essentially for any binary image. And the main reason we did this is primarily because in that case, if I go back to my issues about intractability, I can just, the query set is the same as X essentially. And so I can just learn a generative model on MNIST and then use it for doing all of my calculations. Okay, so let me show you the algorithm in action. So this is going to be the input image to the algorithm, to information pursuit. Yes?
So the query somehow restrict the accuracy of that.
Yeah, you'll see. Let me pause on that because once I finish with the animations, you will see plots about that. So this is a particular input, just to show how IP runs for this particular input. What is here is what are the pieces of the image that the algorithm has seen thus far. It's all gray because nothing has been seen. What is here is the prediction that is being made by the algorithm about the class, 0 to 9, given what's seen thus far. So it's all blue because this is 1 over 10. All classes are equally likely. So what is the most informative 3 by 3 patch for MNIST classification on the entire data set? And so the most informative query after learning all of those generative models and computing mutual information is this one. And happens to be white. And immediately you see that 0 is more likely, 2 is more likely, maybe 6. You can see that a 0 and a 6, all of those are consistent with that patch being white. Okay. Then given that that patch is white, now you select a different one and you keep going. And I'm going to keep going since my battery is about to die. I'm just going to run 9 iterations. You look at it and think about it while I apply my computer.
What is the binary value?
In this particular case, yes, because the images are binary.
What happens if the patch contains both colors?
If the patch,
Contains both colors, white.
no, in this particular case, we're simply thinking of asking 9 queries at a time. It's a 3x3 patch, so we ask 9 simultaneously. But
I think that's one of the here.
There is something here.
One has one.
Blackboard.
here it is. All right, so I hope you've simply appreciated that as the iteration proceed, the algorithm is becoming more and more certain that eventually debates whether it's 0 or 2. But after about 8 queries, it becomes fairly confident that it is a 2. The way in which the queries are selected, again, we can debate as to whether those are the most informative regions or not. But the way to interpret this is really selecting for the purpose of discriminability. So which patch should I look at in order to determine whether this is a 0 or 2 or a. And in this particular case, the algorithm stops after 11 iterations. So then what we can do is to run this algorithm over the entire MNIST data set and compute the expected number of queries that were needed. So for MNIST, it's about 11.
I'm sorry, I just, you go back to slide, I just want to understand how this is used as an explanation. So the classifier says it's a 2, and I say, why is it a 2?
It's a 2 because in this particular case,
And then you show me the middle picture.
yes, it's a 2 because I looked at this region and it was white, and I looked at this other region. That's the explanation in this case, because that's the query set.
Give an example of the wrong.
Huh?
Give an example of the wrong prediction.
I don't hear, I should. I should. But the accuracy is 99.15, so it's probably easy to come up. So now back to your, one of you asked me about accuracy. Yes, there is sacrifice in accuracy. It would be 99.99 for if I train a deep network on the full image. The other thing I want to show is I would conjecture and debatable that tasks like KMNIST and Fashion MNIST and Caltech Silhouette are harder than MNIST. And you can see that the number of patches that are needed is more. So that goes with my conjecture that there is some relationship between task complexity and this semantic entry. Which usually when people tell me, well, how do you measure task complexity? Well, I just measure the accuracy, and my accuracy is lower, then it's more complex. But that's dependent on an algorithm. Here, in principle, right, if I had learned the joint probability model, and I'm doing mutual information, but this is algorithm independent, I'm just computing the theory. In practice, I have some algorithm to learn those generative models. But at least it's not that I'm training a model for classification of them. So I conjecture that this is a more algorithm independent way of measuring that complexity than just looking at the accuracy of a particular algorithm.
Yeah, so I don't want to say the opposite of devil's advocate, but I'm going to play the opposite of devil's advocate, the accuracy. In this case, you are given the queries, which are 3x3 patches.
Yes.
Therefore, you have this accuracy because the queries that you're given are the ones that they're given.
Yeah.
So my point is, like, I mean, you are not compromising, you're compromising accuracy as far as the queries of this one.
Exactly.
So, for example, if you the gods
But,
are okay.
but you're totally right in a sense. If I choose a query set that is overly constrained, my accuracy eventually will go down low. But that goes back to the ideal definition of a query set that is sufficient.
Exactly.
So if I answer all the queries, I should be able to compute the full posterior and get 100% accuracy.
So this is not sufficient.
Well, looking at all the pixels is sufficient.
This is all the pixels, right? You said the answer to it 3 by 3. This is
3
all
by
9
3.
pixels. But you said the answer to that is just all 9 pixels. in 3 by 3.
So what I'm saying is that I've looked at 11 in average, at 11 3 by 3 patterns.
But the queries here are sufficient to recover the whole image in principle. Separately, you don't
Yes.
need to use them.
Yes. I'm just saying I'm using only, but if I were to use them all, then I would get potentially the full
There
accuracy.
is a question.
Yeah.
So from the Zoom, so I'll read it. Are these images all transformed to be binary? And if so, is the runtime impacted when pixel values are between 0 to 255?
Yes. So some data sets are binary by definition, but indeed some of the other images were transformed to be binary. We do not have an implementation of IP that works for non-binary images at the moment. The reason being the difficulty of learning these generative models. And therefore, I cannot answer the question, but more likely the answer is yes, that it will be impacted by having binarized images.
I have a question. So, so these, so what question should I ask in this case? If I really wanted to get an explanation of why, why something say an 8.
I did answer that at the very beginning of the talk by saying that the design of the query set was outside of the scope.
But your mother didn't know what questions to ask. I think this is
For
the patches are really
So,
for data science.
we've debated that a lot, but essentially, at least for computer vision applications, there are many tasks at different levels of semantic resolution. And so for high-level tasks, it sounds very natural that you would ask about the content, what objects are present, what the relationship between objects are. But when your high-level task is already at the level of the object, you could be asking about parts. But for this level of tasks, it's really about the query sets have to be about low-level image information like edges and T-junctions, which are much harder for humans to interpret. So I'm almost arguing that at this level of semantics, we humans don't reason too much at the level of local image structure. Let me, yeah.
So is there a notion similar to confidence in this setting?
Yes, the P of Y given X comes with it.
And it's calibrated as long as queries are good or something like that?
It's calibrated because we are learning full generative models. Maybe I want to get to all of the examples, but since the MNIST is the simplest one, let me quickly go through the others, and then I'll entertain questions at the end. So this is the bird example. There are 12,000 images, 200 classes. They come annotated with 300-ish attributes, and we trained attribute classifiers that go from the images to predict these attributes. So that's a starting point. And then given, so in a sense, we have a query set, and we have classifiers for making predictions for that query set. So given that, we train exactly so the generative model, therefore, in this case, is no longer on the images or on the colors, which I already said we can do because computation treat them. But it's already on the attributes, the answers of the attributes. So this is really a model of the Q of X, which is what I expect. So just to show you one example of how this bird is predicted to be a gray-crested flycatcher. So this shows exactly the run of the algorithm again, the questions that were asked. Black means that the answer was yes, or green, I think, is the answer was yes, and red is that the answer was no. And this means that after 9, well, in fact, after 6 queries, the posterior is already relatively picked. But after 9 queries, I think we have a threshold of 99, and so it predicts it as a great query. Just to answer the question of how accurate this is and what would it be relative to an oracle or relative to an algorithm, just looks at all attributes and whatnot. and how accuracy evolves. So the x-axis is the number of queries we are asking. The y-axis is the accuracy at test time. And just with a few queries, I don't know how many, but it's probably less than 10, we get to the peak accuracy. So you can see there that there is a gap, and it's about, we are doing like 5% less than the state of the art classifier that looks at the whole image.
Is the answer to the quiz is it random, does it have like, because you have a classifier?
There's a classifier, so it's random.
Which
It's random.
is an accuracy
Yes.
itself.
It's random.
So is this randomness any part of the entropy computation?
The algorithm, the design, and everything has been done assuming perfect answers, but the implementation is done with noisy answers. Okay, I'll skip this just to give you one more example. So here we're looking at the Huffington Post data set with 100,000 documents. All documents look like news, like what we have up there. So there's a headline and there's a short description of the news. And there are, I think, 10 different categories: entertainment, politics, food, and whatnot. Here, I think we need to come up with a much better query set. But the query set here was simply, is this word present or not? We came up with, I don't know, the top 1,000 words, and then we ask, is this present or not? And you can see that it's not a great query set because now I'm showing a random algorithm, but rather than saying 1, 2, 3 and stopping at 10 queries as I did thus far, you can see that there are some jumps every now and then, and we need to do 125. So the coding length is much bigger. So showing an example where if the query set is not good, then you're going to need a lot of queries too. And whatever. But again, you can see that it asks whether Donald Trump is or not. It asks a couple of things. Eventually, once the answers easily. Also, another challenge with this is that it's the probability that the answer is yes is very low, whether one word is present. So that's another criteria moving forward on designing good query sets. These are just many more examples, but let me just conclude with one, and this is going to be the last slide: medical diagnostics. Yes.
Question going back to the topic classification.
Yeah.
It seems like the set of positive queries of what words are in the description is a shorter set of queries than some of these.
Mm-hmm.
Isn't just the positive and affirmative kind of tests on the input actually forms a shorter decision tree and all of the information.
Not so sure if I'm following.
Like if I just read the short description, so Margaret Robbie goes,
Yes.
it has like 10 words in it.
Mhm.
So those are the 10 words that would answer positively for. All the rest are not there. Right, so in 10 queries, I know the whole.
Yes, but I would need to. I think it's a great question. I didn't think about that, but let's say I were to do this based only on the short description, and I would hope maybe that the semantic code is the headline, and therefore it selects the words that are sufficient to make the prediction. That could be another way of doing what you're suggesting, but I haven't thought about it in great detail to be able to answer it better. Maybe let's have that discussion after the talk. Last one. This is a medical data set called SIMCAT, where maybe I think just showing the running of the algorithm. So basically, there is a sequence of a long list of symptoms, and this is an example where you initialize the algorithm somehow, unlike the previous example, in the sense that there is an initial positive symptom that is given. That's the way the data set is annotated. And in this case, the goal is to classify what is the disease, and so that's what you see. And this is a running of, so again, we just took the data set, so that comes with the list of symptoms and the answer yes or no for each patient and the corresponding disease. And then we train a VAE for that purpose. And this is the running of the algorithm, the sequence of questions it asks, and whether the answer is yes or no. And I'm running out of time, so I'm not gonna But again, it performs comparable to the state of the art, but it produces an interpretation. And these we've compared with many other algorithms that are based maybe on reinforcement learning or some decision trees, again, demonstrating that we can get to the disease with higher accuracy and much fewer questions, which in the medical domain is important because the questions could be get the results of some test, and therefore each question has a cost. Okay, let me stop there. I hope I've made at least one point clear, which is that I think the way we do interpretability today is not great, and that doing it by design is important, and that doing it in a way that the explanations that are provided are useful to the end user and not just to AI researcher is important. That information pursuit is a friend of that. Sorry for the extra time.